Okay, everybody, so that we can make sure that we're being cognizant of everybody's time, I'm going to go ahead and get started. My name is Jenna Nilo. I am the Director of Marketing and Outreach for Illinois Digital Educators Alliance. Thank you all for coming today. Today we're going to have a webinar on integrating 3D printing in the classroom. In a minute, I will introduce our speaker. But I did just want to go through a few things with everybody. If you could please make sure that you are muted during the webinar so that Desmond has the mic all to himself. If you do have questions, please go ahead and put them in the chat window. And I will be monitoring the back channel for Desmond and interrupting when appropriate. And there will also be a Q&A period at the end of the webinar today so that you will have the opportunity to ask those questions then. And then last but not least, at the end of the webinar, I will be putting in the chat window the link for PDHs. You do earn, if you're an Illinois educator, earn one PDH for today's webinar. So just make sure you stay on till the end, and I will put that in the chat window at the end. So without further ado, I'm going to introduce Desmond Martin. He's the program coordinator with our professional learning partner, NextWaveSTEM, and he is going to take us through integrating 3D printing in the classroom today. So everybody, please welcome Desmond. And Desmond, go ahead, and I'm going to mute myself now.
Awesome. Thanks so much, Jenna, for that introduction. And really glad to be here with everyone. As Jenna mentioned before, I'm Desmond Martin. I'm the program coordinator for NextWaveSTEM. And just a little bit more about myself. I've got a professional background in engineering, graduated from the University of Michigan with a mechanical engineering degree, but really made a change, a pivot towards education. Because in my final year of the program, had a realization that if I worked in industry, I think I was not going to be very satisfied with my job. Always had a passion for young learners and students and emergent technology, especially when it comes to integrating engineering practices into the way that we learn. So I'm really, really fortunate to be working with the NextWaveSTEM as we reach out to educators and really make emerging technology more accessible for students all over the Chicagoland area. So at NextWaveSTEM, just to talk a little bit more about what we do and why we do what we do at NextWaveSTEM, we believe that our world needs young innovators. Basically, we understand that we have some massive problems. Climate change is here. Climate refugees are real. We have them in the United States of America. There are literally millions of families and millions of people all over our country that are dealing with lead in the water supply. We have millions more automobiles on the roads of Metroland Chicago than they were ever designed for, and our national infrastructure has a rating of D-. Not to mention that going back to climate change might end human life as we know it. These are huge, huge problems, and we really think of it on those scales. For us, we know that we need young innovators right away to grow into outstanding innovators and outstanding thought leaders to solve some of these problems. And one way that we know how to go about solving those problems is getting students hands-on with emerging technologies that might help with those solutions as early as humanly possible. But we know that students just don't learn these things by themselves. They need teachers. So we reach out to teachers and empower teachers in these emerging technologies so that you'll groom our next generation of problem solvers. And as Jenna mentioned, before I get too far ahead of myself, if there are questions, feel free to jump into the chat. She'll jump in if the question is really, really good, but don't worry, the chat is completely open. And we'll have some time at the very end to get your questions as well. So whenever we talk about learning and learning new things in particular, we always want to have goals for what we are accomplishing during the course of our time together. And I've got two primary goals for all of us as we sit on the webinar today. The first is that we want to know how 3D printers are going to function and how they can be used in our classroom to support STEM learning. That's really more of the technical, historical, but also thinking about applications that we might have with 3D printers. And this will apply to you if you have a 3D printer or you're thinking about getting a 3D printer. Another goal that we have for our training is that we really want to identify practical approaches for using 3D printers that will help us teach in a holistic way when we think about 21st century skills, but will also help us meet the next generation science standards. We understand that assessment is really important, and having a rigorous way to assess our students while teaching to different modalities and serving the wholeness of who our students are is vital. And 3D printers will really help us do both. I think that we'll find them to be extremely versatile tools. But before I go any further, we always want to give our participants a chance to think about what they're trying to get out of it. So if you're completely new to 3D printing, maybe you're just looking to learn. If you've got a 3D printer in your classroom, you're maybe thinking of some ideas how you might lesson plan and scaffold. If you don't know what you want to get out of it, I want you to take the next 30 to 45 seconds and think about what your own personal goal is and share that in the chat. And I think Jenna is going to help us out by sharing some of our goals with us.
So we've got lesson plans. How do you overcome time constraints? How do we deepen the experience with a 3D printer? New idea for using it this year. How to make 3D printing not just a fun activity, but connected to curricular goals and content. To have a better understanding of what you provide so that we can disseminate your resources to after-school providers. Get out of the toy aspect of 3D printing, how they could enhance lessons. Beginner opportunities to make it meaningful. Your viewpoint on using it in the classroom. Someone's brand new, they inherited a 3D printer, so what are they going to do with it now? Lesson plans, how to apply it in the classroom, how to integrate it. So it sounds like how to really make it useful and integrate it into our lessons is a big one.
Yeah, I'm seeing that as a common theme here, and a common theme that we've had with our educators who we've had a chance to talk with before is really, okay, I've got a 3D printer and I need to figure out what I'm going to do with it here. Like, oftentimes I talk with educators and they say, okay, what's the point of this thing? It's cool and I can make objects spit out, but what am I doing any of this for? And if you fall into that category, I'm really excited because I think we will be able to speak to some of those ideas during the course of the webinar today. So the first thing we want to do is think about what 3D printing is and why it matters. When we think about teaching students and using the 3D printer as a tool, we have to understand that we don't want to use technology for technology's sake. So the next portion of this is going to be a little bit introductory if you haven't, if you've got a very limited familiarity with 3D printing, but hang in there because we will get a chance to talk about ways to scaffold lessons and ways that we can engage our students outside of the toy aspect of 3D printing. 3D printing is the process of taking a three-dimensional design and turning that into a physical object. There are a few different ways to do that. The one that you're going to be most familiar with and the one that you'll see 95% of the time in the student space is what's called FDM, form deposition molding. It's where layers are added in layer on top of layer of a biodegradable plastic. That's a long explanation to say this simple word here, which is called additive manufacturing. It's where we're adding materials onto other materials, as opposed to, of course, subtractive manufacturing. So the really, really exciting thing about 3D printing is that it's different than the way that we've made most of the things that human beings have made throughout the course of history. Usually when we want to make something, we take a large piece of material and we take away from it. We cut it. We take a tree and we cut it down and now it's a log. We take bark off the tree, so now it's a plank. We sand it down and we plane it down. We're removing material, more and more material. We're cutting. There's lots of sawdust or sparks or metal shards or scraps or cuttings left off to the side that will sometimes get recycled and will sometimes be thrown away. That's really what this wood and chisel illustrates, is this board that's becoming a finished piece, but you've got to remove these small amounts of materials that become waste. That's subtractive manufacturing. Additive manufacturing is taking a raw material. In a lot of cases, it's a plastic. In some cases, it can be metal. It can even be plastic kind of mixed with sawdust that will give something that's akin to a wood material that's being added to each other. There's a lot less waste that you have, and you've got a lot more opportunity to customize and make some interesting geometric shapes and patterns with 3D printing. And when we talk about emergent technology, 3D printing is a relatively young technology. Really the first modern additive manufacturing techniques that we see are developed in Japan in 1981. So really within a generation, we've seen the genesis of this technology now going into more application. The STL file format, stereolithography, was invented by a company called 3D Systems to do 3D printing in 1984. And then the most common printer now, the FDM or FFF 3D printing method, is developed in 1988, which means that it's actually younger than I am. In the mid-90s, we saw patents start to expire, and that's why we have a range of 3D printers that are available now. If you go online and you look at different manufacturers, you can get into 3D printing for as little as a couple of $100, and there are manufacturers who are developing 3D printers both for commercial use and for educational use. On the education side, you could usually see a 3D printer about a couple $1,000s, maybe $2,500, up to about $10,000 on the educational side. And if you're getting more professional, your 3D printer will then start costing tens of thousands of dollars to hundreds of thousands of dollars. So it's all about what you need and why you need it. For your average school, staying in the four-figure range is really going to get you to where you need. But once again, we always want to focus on the fact that we're not just teaching technology for technology's sake. 3D printing is real. In fact, Forbes magazine every year does a state of 3D printing report where they think more deeply and analyze the data on how 3D printers are being used. The latest available data was from May 2018, and it found that prototyping, 55% of the time, is what we're seeing 3D printers used for. Whenever we're manufacturing a new physical object for mass market, there is an entire design process, an engineering design process. Depending on how you're being taught at your local school level, and depending on your methodology, that design process might have 5 steps, might have 7 steps, might have 11 steps. But one commonality in all those design processes is the prototyping process. It's integral. You can't get rid of it. You can't push it off to the side. And you can't make a good product without prototyping first. But increasingly, we're seeing production, the actual production of the final product, more and more move towards additive manufacturing techniques. And then in the more architectural space, the proof of concept model, being able to visualize a much, much larger solution on a micro scale quickly, are really applications that we see more and more being used in 3D printing. So the direct connection that we can really make between 3D printing and what our students are learning is the fact that they will be learning more about the product design process. And that's going to be vitally important when we think about the way that our students are going to design solutions later on. So I know I mentioned a little bit about this later on, but this GIF gives a much better example of what's happening here. How do 3D printers work? 3D printers work by taking a 3D file. Usually it's an STL, stands for stereolithography, and actually doing the math and slicing that file into individual layers. The 3D printer then has the material, usually biodegradable plastic, loaded into it, and actually acts as a very precise hot glue gun, for lack of a better description. It's going to milk that plastic down into layers as thin as about 1/5 of a millimeter, and then it's going to run those layers on top of each other, which is kind of what you see in this photo here. Each layer, and for this hand, it's going to be thousands of layers actually laid down one on top of each other, and it's hardening over time, giving us a precise object. There's a multitude of different softwares that we can use to do 3D design. One software that I'm a huge proponent of, and that I know many of our participants may already be familiar with, is called Tinkercad. Tinkercad is owned by a larger company called Autodesk. Tinkercad is completely free to use, has really good resources that will allow you to grow in your ability to use 3D printing. For the curriculum that we develop here at NextWaveSTEM, we utilize Tinkercad. Also, another companion you could think about with Tinkercad is actually Fusion 360. Fusion 360 is a much more powerful 3D software editor, also owned by Autodesk, and because they have those products underneath an umbrella, you can actually export the designs that you make on Tinkercad over to Fusion 360 and continue to innovate on those designs. Depending on your 3D printer, you can export that STL file, and your 3D printer will have its own software that is actually called a slicer. The slicer will take that 3D printable file, slice it according to what your machine needs exactly, and then begin printing it. And the print time will vary depending on how big the print is. Usually any place from about an hour to, if you've got something much more detailed, if you've got many objects that you want to print off, multiple hours. Multiple meaning 6, 7, 12 plus hours. It all depends on the complexity and the amount that you're printing. But of course, as we grow, we're seeing many more interesting applications for 3D printers, some things that really were in the realm of science fiction. Right now, it's mainly for engineering prototypes, but we're seeing very advanced applications in 3D printing as well. The picture that you see on the left is actually of a 3D printed metal rocket engine. This engine and nozzle is all one piece. Which is really huge because that means as we have a change of expansion thermally in space, we're having a part that's less likely to break, which is much more reliable, also lighter. But we're also seeing companies experiment with actual biological materials. So there are companies that are synthesizing cells that can be laid into layers to 3D print organs. We don't see any organs being placed inside any living creatures yet, but this is something that we're trying to do. We're trying to figure out more and more advanced ways of using this technology to solve some really pressing issues. But of course, all that is great. What are some tangible 3D printing and computer-aided design applications that we can point our students toward? Well, most of us are in Illinois, which means we're very familiar with this building, and all of our students are familiar with this building. It's the Willis Tower. If you're young enough not to know any better, if you are older, then you know it as the Sears Tower. And the amazing thing about the Sears Tower is it's a cultural landmark. Everyone can look at it and know what it is, but my favorite thing about the Sears Tower / Willis Tower is that it is built in the internationalist style, which is a subset of modernism. Modernists are really cool when we think about design because they like straight lines and boxes and things that are really actually relatively easy to design and model. So believe it or not, the Sears Tower is actually not one tower, but it's 9 towers. And those 9 towers are all made up of squares that are pulled out to different heights. This is actually a chart that shows the way that these different, they call them bundled tube structures, the way that these towers are aligned together, and the way that they're pulled out to their different heights, forming what is actually the Sears Tower. Really, really cool design, really, really simple design, really, really iconic design. And if we can see something like this, now we can open up the world of architectural design processes for our students as well. Something that they know really well, we can break down and we can chop up into a model that they can design themselves. So what we would have them do as a part of one of our lessons in the curricula is actually model this. Thinking about how we see the shapes, how we see the structures, how we see the geometries, and then get them into a 3D modeling software like Tinkercad. By pulling out simple boxes and arranging them in that 3x3 grid, we can create this model of the Sears Tower. Something as simple as this can really introduce them to using a tool to do architectural design, but also gets them familiar with using a tool like Tinkercad, where it's very simple to drag and drop your shapes and create these bundles of shapes that will represent different architectural pieces. So it's really, really fun, really, really interesting for our students to take something that seemed like it was on a huge scale. Some of them might be even intimidated by saying, okay, I want to design some element or recreate this design. But once you peel back the layers, you can show them that these design elements are really not beyond them at all. So now I want to give us another moment here and consider our students. And really the questions that we might have from our student perspectives, because we asked some really good questions that we have faced in our classrooms previously. What are some of those equipment and limitations that we might face? How do we need to plan with respect to experiencing the 3D print being made, and how can we deal with it if a print fails? All these things are critical when we think about 3D printing. And I see some other really, really good questions here about 3D printing as well.
I was going to say, we also have a question that goes along with that. A lot of students want to just download the ready-made 3D print design. Any tips to move them towards creation? So how do we get them out of that mindset of just downloading the what's out there online and actually having them create something as well?
Really, really good question. The best thing I can say towards that is really thinking about functionality and ownership. It's one thing for me to see a cell phone case and say, okay, I want the cell phone case because I need a cell phone case and I can easily pull something offline and print it. And I really can't fault students for that. That's simply, okay, doing something that's utilitarian and then making it for myself so I can consume it. That's still really in the consumer mindset. What we want our students to do is really become invested in why they would create something with a 3D printer, which is why going through a design process is so important. Another lesson that we really like to get our students started with when it comes to ownership and personalization is the idea of designing their own keychain. And it's a really fun project, and students will jump into it right away. And they won't just download their own keychain because they know it's theirs. It's going to have their name on it. It's going to be personalized. It's going to be customized. So going through a design process where students understand why they're making an object and knowing that nobody else has considered this scenario, it's for them, by them, really breaks them out of that mode of trying to just quickly pull something down from the internet. It's a really good question. Other good questions that we have up here, when we think about the equipment limitations for the classroom, one thing that we have to keep in mind is that print times are long. So part of this is managing expectations. The design process is also helpful with that. The 3D printers will take time to print an object. Letting our students know that it's not realistic to think of our 3D printing technology as a paper printer is really important, because when you come in on day one, students will be thinking, hey, we're in a 3D printing class, we're gonna 3D print stuff, I'm gonna walk out of here on day one with a 3D printed object. And we have to kind of pull them down to the reality of the process that we have to design, that we have to set up, that we have to slice, that we have to have a 3D printer working over an amount of time. That's a logistical challenge for our teachers. If you've got a classroom full of 30 students and students are designing objects that take 2 or 3 hours to print, congratulations, you've got 90 hours of time where the printer is going to be running. And that's something that you have to budget for. So you might only have one print going out of your printer for a class for a week. And structuring your lessons so that you're doing design elements, that you're doing elements where you're testing user cases, or you're gathering data, or you're testing what you print over the course of the week in between the time of your printing or where the printer is going, is really, really important. If you've got access to multiple printers, that makes a big deal too. Some of us work in districts and areas where we can go to our local libraries and they've got printers and down printing time. They're able to help us with those. So it's about understanding your resources and what you have around you as well. Another thing that's really important to consider is that the technology is still really young, and that means that things will fail. One thing that is kind of heartbreaking the first time you experience it is when you set up your printer, you've got multiple items going, you might have 6 things printing out. It takes 3 hours to print, so you get your printer going, you go off and you teach your next set of classes, or you go for lunch and you come back and you see a spaghetti string ball mess where something is going wrong with your 3D printer. It's okay, how do I deal with this? That once again goes to understanding the machine and talking to our students about the process of printing, what's going on, the actual process and the differences of temperatures of what's going on inside the printer, and explaining to our students that failures are part of this process. So now we've got to really change the way that we design, or become a little bit more knowledgeable about the environmental factors that happen when our printers aren't working. Quick anecdote about that, working in our offices, we moved into a new office in May, and we moved all of our 3D printers, had a 3D printer in the office, and for 2 weeks could not get it to print correctly. We'd have it going, and about 45 minutes in, and we get the spaghetti string ball of mess, and had to do some Googling, had to look at manuals, and learned that it was actually 2 coals in our office to properly 3D print. The air conditioning was blowing really hard. It was blowing a draft, and it was causing our printers to misprint. I moved the printers to a room without an air conditioning vent, and our prints came out perfectly. So this is a chance for exploration and investigation, not only for you as a teacher, but for students as well. Okay.
Desmond, a little off topic, but I do have a question here. My printer uses PLA filament and it seems odorless, but I keep hearing there are still chemicals emitted into the air, that it isn't as safe as originally thought. Do you know more about this, and do I need to work on adding in a ventilation system?
Really good question. Sometimes there is a little bit of a smell with the PLA filament. So PLA is safe. It is biodegradable. It is a bioplastic. That means that those odors aren't something that you have to be worried about in terms of chemical contamination for your students. The MakerBot brand of PLA actually smells a little bit like maple syrup as it's coming off the printer. That's nothing that you have to be worried too much about. Now, if you decide to branch out into some other materials, PET, for example, is the same plastic material that is used in water bottles, and you can also buy rolls of that to print. It's a little bit stiffer, a little bit stronger, but those chemicals you might have to worry about. As long as you're printing with PLA, your students should be fine, and ventilation is something that you shouldn't have to worry about too much. That is a great question. So now that we've covered a lot of the basics and we've thought about the way that we all use 3D printers from a mechanical standpoint, what's happening with the printer, what's going on, now what we want to do is think about performance, tasks, and brainstorming instruction. This is the part where we're thinking about how we would develop lesson plans or units, or how our 3D printers can really aid in some of the other teaching that we're doing if we're teaching across disciplines as well. So what I've done to help us do that is I've pulled out 3 standards from the next generation science standards. And these standards deal specifically with the engineering design standards. I've pulled them from 3 different levels, and we can talk a little bit how these 3D printers can help us in these standards. So for the engineering design standard 3-5, ETS 1-1, the standard is that they will define a simple design problem reflecting a need or want that includes a specified criteria for success, constraints on materials, time, or cost. One thing that we have to consider as we are going through these standards is how we're going to assess these standards. How will the students show us that they are able to do what the standard is asking for? And then the performance tasks that build up to this. When we think about this idea of defining a simple problem, that's really the core part of the engineering design process when we think about a user story. What's something that has to get fixed? What's something that has to be made better? What's something that we just wish we could make better and that we want to apply our understanding of science, math, and technology to make it better? So a perfect example is that students at a particular school, a group of 3rd grade students, had an issue with their water fountain. Their water fountain was too high. They couldn't reach their water fountain. They could not drink from the water fountain. So there they have a problem. There's a simple design problem. The water fountain was not designed for my height. So when it comes to the criteria for success, we know that we want to create some kind of solution that will allow our students to reach the water fountain to be able to drink. We know that we can set the constraints of materials and time and cost arbitrarily. So when it comes to our 3D printer, many 3D printing software will allow us to actually do estimates on the amount of time that the printer will actually be printing. And we can kind of subdivide that, thinking more holistically around not necessarily print time, but the time spent in the design process and the time towards the solution. Do we want to solve this problem by the end of the day, by the end of tomorrow, or by the end of the week? And then many software will give us estimations when we think about how much the raw material will actually cost. 3D printing filament, generally speaking, when we're thinking of PLA, you can purchase a kilogram of PLA for about $15 to $17. And if I were to put that in terms, we could understand a little bit better. You could probably print over 100 key rings. Well over 100 key rings from that 1 kilogram of PLA. So you've got some material to work with, and you can apply some mathematical reasoning to that as well. So when you think about assessing these standards, there are different practices that we have for our students. We can do them as a group. When we think about our elementary students, where they're sharing and they are presenting these standards, these problems, I should say. The problem they're presenting would be about the water fountain. They could be sharing their anecdotal experiences about the water fountain, or they could be actually taking measurements about how much shorter they are than the water fountain, so that they're actually quantifying the problem. When we think about performance tasks leading up to the assessment, the assessment or the general performance task for the students, one way we're thinking about that is actually identifying problems. And for our younger students, this is actually really fun and really easy because there's a snowball effect. I like to ask the question of the students in a really, really fun and non-judgmental way. Hey, what in this school needs to be better? And if that doesn't work, hey, what in our school don't you like? So almost immediately, there are hands that will shoot up. Oh, I think the lunch could be better. My locker is too small. I think our class periods should be longer. Some of those problems are process problems. Some of those problems are problems that we can't solve with technology per se, but other things like, for example, my water fountain is too tall, my locker is too small, I don't not have enough space on the playground. Those are physical problems. And that's where we think about using a 3D printer to create a physical solution. So those tasks leading up are identifying problems, identifying who's having those problems, and then how we can actually assess those problems and then move into the later parts of the design process. Now, the third part of this, when we think about our standards, how we're going to foster 21st century skills is really important because that's talking about a more holistic student. When we're thinking about 21st century skills, we're thinking about skills in creativity and collaboration. And some of those things we're going to be doing are going to be really important when we think about how we communicate those problems, not only to our instructor who's doing the assessment, but also to each other. Can you really accurately state why your problem is a problem or how it's a problem? Can you engage in a debate, in a debate about the problem and whether or not one problem is more pressing than another? So we can see even at that elementary level that the 3D printer becomes a tool in the design process that allows us to answer the question, okay, what's the problem and what's a potential way that we can go about solving it, which is really at the heart of engineering. A shorthand that I like to use for engineering is that engineers are just professional problem solvers. Engineers use science, technology, and mathematics to solve problems. So at the middle school, we see our standards start to evolve a little bit into something that can be more process related. Our middle school standard says that we're evaluating competing design solutions using a systematic process to determine how well they meet the criteria and constraints of the problem. Now, this standard is one of my favorite standards because of the key word here, competing. I love competitions. I grew up playing sports. I was always competitive, even to a fault. And it's really fun to have our students thinking about the fact that what they're designing maybe for a particular problem, but not all solutions are necessarily created equal. For our students, we're developing these processes where they can really think about how well a job they're meeting the goals of these problems. So how will we assess these standards? Well, for our students, it's about learning the design process and actually building a rubric themselves. If I've got a problem, and the problem can be arbitrarily defined either by the student or by the teacher. Let's say that I need to figure out a faster way to get myself up the hallway. I've got a hard time passing classes. I need to figure out a way to go faster that isn't me running down the hallway. Well, students might try to design and build a physical solution for that, something involving wheels, from vehicle designers that are emerging from this particular design solution. Well, now we've got all kinds of things that we need to assess as to whether or not the design is a good design. Is the design actually physically convenient? We have to decide now what the dimensions, the optimal dimensions for the design will be. Will the design take up too much materials or too much time? Do we need to consider ways to actually decrease the amount of time and material that students are using, or can they be more liberal with the amount of PLA and the amount of time that they take? We get to set those standards. Can we also think about ways in which students will then talk about the actual efficacy of their design solution. Is this wagon or tray or sled or whatever we want to call it actually safe